So in this module, we're going to look at the game from a modular design standpoint. What we mean by that is we will design our system using three important tools. The first one will be a call graph. The second will be a data flow graph. And the third will be a low-level detail of flowcharts.
Professor Yerraballi, why is modular design important?
So modular design allows us to manage the complexity of a large project. This project is going to be one of the largest that you will handle in this class. So what we want to do is be able to manage by modularizing, which means that we break down our system into small modules. This will allow us to manage change. It will allow us to debug easily, because if we break them up into small modules, we test one module, we're sure it works, and then we can hide that module as if it were a box and work around it and see other modules. As I said, it allows us to manage complexity. So now we'll look at each of these in turn. We will look at the game overall and break it down into modules, where each module will be specified either as a circle if it's a software, or a square if it's hardware. And we will describe which module calls which module by using arrows. This is what our call graph is going to be like.
What are the three files that one normally creates for a software module?
The software module is going to be managed by three files. So let's take an example of the ADC module. So when we look at a module like ADC, we will have the specification of the module in a ADC.h.
And what's in the H file?
The H file lists the public functions as prototypes.
So these are the functions that another module could call.
That is correct. So this is what the module exposes to the outside world. So we'll list all the functions, and not just functions. If there's any other data that needs to be exposed, that's also going to be exposed in the header, as we call it. And then we will have an ADC.c, which will be the implementation.
So this is where the code that actually runs exists.
That is correct. And we want to hide the implementation and expose only the public function. As we saw, this allows us the flexibility of improving the implementation or changing the implementation without changing how the users call this module.
But what's the third file?
Okay. And the third file is not specific to the module itself, but how is the module used. So the main.c, in our case, is going to be the driver that will call this module. The driver is also sometimes the tester of the module.
So this file explicitly shows how we're going to use the module and how we tested the module.
That is correct. And so at times when we were developing the code, we will have in the main.c specific testing code for each module that we are building. And we test that module, and then we discard that piece of code, and we keep writing new testing software.
Okay. Professor Yerraballi, are there any guidelines in developing modular code?
The there are guidelines. These are something that you learn by practice, but the general idea is to maximize the number of modules by making sure that you minimize the interdependency.
Give me some examples. What do you mean by interdependency?
So the first idea is the idea of maximizing modules means that I'm going to have as many modules as it takes to break down the problem in a divide and conquer sort of way. That is, I'm going to break it into one module, another module. If I feel like some functionality needs its own module, I'm going to build another module for it. But by interdependency, we mean modules are going to exchange information. So there's going to be modules communicating with each other. This module may call this module may in turn call this module. But part of this is how much data, so how much data do they exchange? The volume of the data, if you will, that they exchange. Now, we want to make sure that these modules are not exchanging huge amounts of data. And if two modules are exchanging a lot of data, maybe there's some reason to think of them as one single module. And so we want to maximize number of modules, but we also want to minimize interdependency, because the exchange of data between modules, when it gets too much, the communication becomes a bottleneck.
So let's look at modularity from the perspective of our game. Where do we begin?
So as I said, the first thing we're going to look at is the call graph. So for our game, the heart of our game is going to be our game engine.
So this is the main code that controls all of the game functions.
That is correct. And so this game engine is going to be using a bunch of different modules. The first module I'm going to look at is the ADC module. So the ADC module will encapsulate all functionality related to the slide pod. Remember, the slide pod is a piece of hardware, so I'm going to write it like that. So this is encapsulating the information that we specify for the slide pod.
What does that arrow mean you just drew?
So the arrow is the call, the interface where we say that the game engine calls the ADC module, which calls the hardware, which is our slide pod.
Okay.
So our second module we're going to look at is the switch hardware. Switch hardware.
These are our buttons.
These are our buttons. So all the buttons, all the switches that we have on our system are going to be managed by this module. The third module, obviously we want our game to be fun and it should sound fun, so we're going to have a sound module. And the sound module will interact with a piece of hardware which is going to be our DAC, which, as you remember, is going to be connected to the headphones. So the last module is going to be our Nokia display module, which is a Nokia 5110. So this is our display module. This is going to be responsible for all the graphics, and it's going to be interfacing with our Nokia display 5110 hardware LCD display. Okay, so we're indicating that simulated hardware by this here, which is a cross between a square and an O and a circle.
You just invented something,
Yeah.
Professor Yerraballi.
I did.
A circle square.
Circle square. So now that we saw the call graph, John, do you see any interesting things about this graph?
I see that we have 5 modules. 1, 2, 3, 4, 5. But there are only 4 arrows between this. This means that we have a lot of modules and very little interdependence. The switch doesn't call sound, the Nokia doesn't call the ADC, and the ADC doesn't call the game engine. This is a very simple call graph.
Okay, so we saw the call graph. Now let's look at the data flow graph.
The data flow graph is another way to visualize the modularity.
So we kind of recreated the call graph with the 5 modules. Our 5 modules are our game engine, our ADC, our switch, sound, and the Nokia 5110 module. Now we're going to see what the real exchange is going to be. So let's look at one of them. I see the slide pot, which is going to give us a position, and we take the position and we convert it into a voltage, and we do this at a 30 hertz. And what happens as I get this voltage into my system is it's going to convert it to a 12-bit number, and the 12-bit number is our measure of the position on the slide pot.
Okay. But in a data flow graph, what do the arrows mean this time?
So the arrows in the data flow graph is the passage of information or data. So in our case, the position is moved, which is a resistance, if you will, is going to be converted to a voltage, which is moving from the slide pot to the ADC, which is a 0 to 3 volts, which is moving from the ADC to the driver, which is then moving from the driver to the game engine. So it's the passage of information.
Okay, and I can see we're passing 12 bits 30 times a second.
That is correct. And so the other modules we'll see, we can quickly list. So there are 2 inputs, are 2 switches.
Yes.
And then that is also being read at 30 hertz, and which is going to be the 2 bits of information. The 2 switches are 2 bits. We pass that to the game engine. These 2 together are what I think of as our interface, and the interface is being sampled at 30 hertz by using the SysTick interrupt. And this is what comes into the system, and this is what goes out of the system, which is a sound, which in our case is going to be 11 kilohertz. Obviously, sound requires a more demanding timing, so we have that flowing the other way. So you see that there's a 4-bit, we're using a 4-bit DAC. So the 4 bits go from the sound routine to the sound module to the DAC, which is then fed to the headphones as a single analog signal. And so this is our sound, which will also be managed by a timing module, which is a timer, which we will going to look at later.
Well, so far, you've just put the pieces together from the last 3 labs. But what's new in this lab?
Okay, so the new thing in this lab is the graphics. And the graphics are part of the display, the LCD display, which is the Nokia display. And we will try and abstract all the low-level details so that we can think of this as simply calling certain routines that either display an image, clear the buffer, or redisplay a new buffer. So the third piece of our design, modular design, is flowcharts.
The flowchart is a way to describe a software algorithm. And you don't have to follow this explicitly, but this is our advice on how we build our games. Every software needs a main loop. Okay, so we have our main loop, which will begin when we hit the button. As all embedded systems, we will begin our main loop with initializations. So we'll initialize the PLL, the graphics, the DAC, the switches, the A to D converter. We'll initialize all of the components of our game. And then after we've initialized everything, we will enable interrupts. And this way, all the initializations will be complete before the interrupts are turned on. In order to make the game extremely interactive, our recommendation is that you do the LCD outputs, the graphical outputs. Do all the graphical output in the main loop in what we call the foreground. So this is the foreground thread here, which executes when there's no interrupts. Of all the things we do, the LCD output will be the slowest. It'll take on the order of milliseconds to generate actual output to the graphics. The other two things we're going to do is things that occur very, very slowly, and this will be assistic interrupts occurring at 30 hertz. 30 hertz is fast enough that our eyes can't tell it's moved. 30 hertz is right at that range where it will look smooth. And in our assistic interrupt service routine is where the actual game engine will occur. And so your game, whatever it is going to look at the switches and do whatever it is supposed to happen with those switches. You'll look at the A to D converter, the slide pot, and do whatever your game is supposed to do with the slide pot.
Maybe movement.
Yeah, like moving your ship around, firing missiles, whatever is supposed to happen in your game. And then we will decide to move sprites. And a sprite we'll define later, but a sprite is one of the objects of your game, one of the virtual elements of your game. We will decide to move it. Now we're not doing the graphics, we're just deciding where to draw all the sprites.
So the movement is a virtual movement. The physical movement is always done by the main program by rendering this movement on the screen.
Yes, and this is a virtual movement. And you notice the flowchart of my assistic interrupt service routine follows the classic arrows only go down. This way, the execution time of this interrupt service routine will be short and bounded. One of the reasons we have threads is so we can separate or define individual software processes. And the other process, the other action that we want to create is sound. And so we are going to separate the thread which produces sound from the thread which plays the game by using two interrupt service routines. This interrupt service routine is going to run a lot faster. It's going to run at 11 kilohertz and generate a sound. And so if it's time, or if we wish to play a sound, we will do the output to a DAC. And if we wish to not play a sound, we won't do an output to the DAC. And notice that this interrupt service routine separates the action of playing the sound, separates it from the action of playing the game.
So you're saying that it's possible that when I choose to fire, I want to produce a sound.
Yeah.
And so I schedule the action, but the action itself is performed in the timer to a ISR.
Excellent. So we could start a sound in our game, but the actual sound is going to occur with a second interrupt occurring at a much faster rate.
This will also allow us to change sounds from one sound to another sound depending upon what action has caused the sound.
Absolutely.
All right, so we've looked at the design. We've delved into the three aspects of design, which are our call graph, our data flow graph and flowcharts, and we are now going to look at some details that we haven't covered yet in the previous chapters.